time is largely going to be on graphing polynomials, which is something that you've done before. You graphed polynomials in college algebra, but back in college algebra you had a calculator, right? Now we're going to talk about how to graph them without the calculator. How can we find out all those pieces of information without using a graphing calculator to assist us? So our first step, we'll start out with something that we've talked about before, maximums and minimums. So these are optimization. Some of them I may ask you, we've done some with word problems a little bit. Our focus right now is mostly going to be on the graph, but some uses for this. It's not just something we do for no reason. Actual scenarios where this is used in manufacturing, if you want to create a shape that minimizes your manufacturing costs, you know how much it has to hold, but how should I design this so it costs me as little as possible? The maximum acceleration of a space shuttle. In medical field, what's the radius of a contracted windpipe that expels some air most rapidly during a cough? At what angle should blood vessels branch so as to minimize the energy expended by the heart in pumping blood? So there are actual scenarios that involve this calculation. Now we're not getting into these. Some of those would involve some very nasty equations, so we're probably not going to get to those, but we're just learning the process right now. Okay, absolute max, absolute min. All that means, an absolute max is the actual highest on the entire graph. An absolute min is the lowest on the entire graph. We have local maxes and mins and absolute maxes and mins. The absolute applies to the entire graph. Here, my absolute max would be f of 3 equals 5, root of 0.35. My absolute min is right here. Sometimes these are called global maxes and mins. If I ask you to find extreme values, I'm talking about maxes or mins. The big thing on these is they can be endpoints. And when I talk about local maxes and mins, they cannot. But the absolute, when I'm dealing with the entire graph, it can be an endpoint. And when I talk about local maxes or mins, they're not higher or lower than everything on the graph, just the points immediately surrounding them. So for instance, on this graph, we have a lot of points. This one right here would be a local max. It's not the highest on the entire graph, but it's higher than the points surrounding it. This would be a local min. This one, it's a local, but it is also the absolute max on the graph, assuming these are endpoints and my graph doesn't continue. So it can be both. This would be a local min. Local maxes and mins can't be endpoints. So the absolute can, but the local cannot. So this last point, I cannot call that a local max. Do I have an absolute min on this graph? Are you sure? I do. Where? This first endpoint. Absolute can be at the endpoints, and you see that is the lowest the graph ever hit. So this one is the absolute min. Any questions so far? Let's look and see. If I want the maximum and minimum values of x squared, how could I figure that out? What? Sketch a graph. We know what x squared looks like, don't we? What is it? Parabola. And we know it keeps going up forever both ways. Does it have an absolute max? No. Does it have a local max? No. What about minimums? Yes. This one right here, f of 0 equals 0. That is both an absolute and a local minimum. There is no max in this graph. What if I said x cubed? So if I graph it, x cubed is the chair. Does it have any local or global max or mins? No. Let's use a graph to identify these. And I apologize, my projector is so awful you can't even see my graph up here. Can you guys see the one on your paper better? So. Okay, the absolute max. Do we have a highest on our entire graph here? Yeah. F of 4 equals 3. So the 0.43 is the absolute max. The absolute minimum. The lowest point on my entire graph is down here. I don't know if you can tell, this is an open circle. If it is an open circle, does it count? No. So my absolute min? There is none. So local max. There can be multiple of these. So we're looking for points that are higher than those around them. So I see right here, but what's wrong with that one? It's an open circle, so it doesn't count. Right here, that one is closed. Is it higher than the points on both sides of it? Yeah. So I have a local max at f of 0 equals -1. It's not an endpoint for the entire graph, so it's okay. Any other local maximums? What about my absolute max? That's also a local? Okay, local minimum. I can't use endpoints for the locals. I'm looking for points that are lower than those immediately surrounding them. So if you look right here, this closed circle, the points on either side of it, aren't they above that one? So this point is itself a local min. F of -4 equals -2. Where else? F of -2 equals -3. at 0, this one would be, except it's open, so it doesn't count. This one wouldn't work because it's open. So that's it. Questions there? Let's draw a graph. So I need a graph that has an absolute maximum at 5, absolute minimum at 2, local max at 3, and local min at 4. This graph is not unique. There are lots of options we can draw. Absolute max at 5. So when x equals 5, I have to have a high point here. And absolute min at 2. So at 2 I have some low point. Those are absolute, so I can't go above or below those points. A local max at 3, local mins at 2 and 4. So let's start here. So my graph would have to come down and hit this, and I can't ever go below this point again. That is a local min and my absolute min, so I've got that. At 3, I need a local max, and at 4, I need a local min. So what's going to happen is my graph's going to go up. At 3, it's got to curve and come back down, and at 4, it's got to curve and go back up and hit my absolute. Now, could it keep going past my 5? It would have to at least turn back the other way. Absolute maxes can be endpoints, so that's okay that it is. My suggestion on these is when you finish your graph, just read back through the requirements and make sure your graph meets all of those, because there are lots of correct answers that we could draw here. Any questions there? So now we get to the extreme value theorem. It tells us if our function is continuous on a closed interval, so no breaks in our graph, then it will have to have an absolute max and min in that interval. The only way this works is if you have a closed interval, if we have a definite starting and stopping point, so our graph can't keep extending either direction. So here's just a few graphs. Again, it was a closed interval, so we had to start and stop somewhere. We can't have arrows on the end. So we can see this graph, we have an absolute max, absolute min. Absolute max, absolute min could be the endpoint. This one, the absolute max, you hit the same value twice, so it has 2 absolute maxes, and then the 1 absolute min. So if we're going to draw our graphs, we need to be able to find those values. Think about what you know. If you were looking at this one, what happens with those maximum and minimum values? The slope of the tangent line is 0. How do we find the slope of a tangent line? The derivative. I put a couple examples on here of why it doesn't work if you don't have a continuous function. You know, if there's a break in the graph. This one wouldn't have a maximum because there's an empty circle there. This one, it's approaching a vertical asymptote, so there's no maximum. So it does require continuous functions. But we can find it because we have those horizontal tangent lines. So if you have a local maximum or minimum, and if the derivative exists, then the derivative will equal 0. Very, very important. This is what we're going to be using on most of the problems that we do today. Now here's my question. If the derivative is 0, does that guarantee the point is the maximum or minimum? No. If you think about x cubed, if you did the derivative of x cubed, you get 3x squared. If you set that equal to 0, you get 0. So when x is 0, we have a horizontal tangent line, but is 0 a maximum or a minimum? No. So if it's a maximum or minimum, the derivative equals 0. But if the derivative is 0, that doesn't guarantee anything. It is also possible for these maximums and minimums to happen when the derivative doesn't exist. Think about absolute value. We talked about when we did derivatives that it doesn't exist at sharp corners because there's not a unique tangent line there. I think we would all agree that this point is the minimum on our graph. But what happens is the derivative at 0 doesn't exist. You know, when we do with absolute values, we use the piecewise function. And what happens is when we do this derivative, those two pieces don't match up. The first one has a derivative of 1, second one has a derivative of -1. And so the derivative at 0 itself does not exist. So we can have a maximum or minimum when the derivative is 0, but also when the derivative doesn't exist. The term that I will be using a lot for the next few weeks is critical numbers. A critical number is anywhere that the derivative is 0 or does not exist. And those are the points where we have our maximums and minimums. So for the rest of the day, we are going to be looking at functions and finding critical numbers for those functions. Here is our first one. I want all the critical numbers of this function. To find critical numbers, we have to do the derivative. What should I do to this probably before I find the derivative? What would make it a little easier? If I do the derivative right now, I'm going to have to use the product rule. Would you rather distribute first so we don't have to do product rule? So that's 4x to the 3/5 minus, when you multiply these, you add exponents. So 1 plus 3/5 would be 8/5. So now we do the derivative. Exponent comes down, 4 times 3/5 is 12/5. X, subtract 1 from the power, 3/5 minus 5/5 is a -2/5. Minus 8/5 x, if you subtract 5/5 from that, you get 3/5. I have to find out anywhere this is 0 or undefined. So it might help you to rewrite it a little bit. A negative power puts it on the bottom. Okay. How would I I find out what makes this equal 0? I need to know when this equals 0. What could we do to solve that? It's not really a trick question. I mean, to solve this, what would you do? Add over. Then we could cross multiply. X to the 2/5 times x to the 3/5. If you add 2/5 plus 3/5, that gives you a 1. And we get 3 over 2. So my critical points, or critical numbers, are when x is 3/2. That's what makes it 0. Looking back at this, is there anywhere the derivative doesn't exist? Is there some value of x that would make this undefined? 0, right? If you plug in a 0, you get 0 on the bottom of a fraction. So that is also a critical number. Your critical numbers are where the derivative is 0 or undefined. So that's all we had to do there. Questions there? If I want to find maximums or minimums, I told you if the interval was closed, we had to have them. So what we'll do is find all the critical numbers, and then we're basically going to test. We'll take the endpoints and the critical numbers and plug them into the original. Whichever one gives us the highest y value is our maximum. Whichever one gives us the lowest y value is our minimum. So I want to find the absolute maximum and minimum of this function. First step to do that is to find the critical points. So we need the derivative. This is a polynomial, so a nice easy derivative, 3x squared minus 6x. Is this ever going to be undefined? No. If you have a fraction, you need to think about the denominator, but if it's polynomial, it's always defined. So I just need to know what makes this equal 0. What could I pull out of here? Take out 3x. That leaves us with x minus 2. So the critical points. What are the numbers that make x, or make this equal 0? 0 and 2. Okay. So we found our critical points. Now we are going to test the endpoints and these critical points. You do need to watch. If I had a critical point of like 6, would I use it? No, because my interval was only from -1/2 to 4. So if you get a critical point that is not in your interval, you're just going to ignore it. I'm just going to plug these into the original equation and see what I get out. So if I put in a -1/2, is that right? Is anybody testing this, or are you just waiting for me to tell you the answer? I think. If we plug in a 0, what do we get out? 1. If I put in a 2, I get 8 times -3. And if I put in a 4, negative, or positive 17. Now this isn't going to tell me my local maximums or minimums, but it'll tell me my absolute. What's my absolute min? Absolute max? 17. Are there questions on so I have a lot of examples on here. We may or may not do them all. Let's do, may do 1 or 2 more before I stop for today. Does f of x equals 2x attain a maximum and minimum value on interval 0 less than or equal to x is less than 1? Let's draw a picture. If I plug a 0 in this, 2 times 0 is 0. If I plug in a 1, 2 times 1 is 2. 2x is just a line, isn't it? But what would I have to put at the point 1, 2? Open circle, because it's not equal to. So does this have an absolute min? It has a min. Does it have a min, max? No. Okay, how come? I told you we had that theorem that said it should. Why didn't this one? Yep, the open circle. It has to be 2 closed circles for it to work. Okay. Let's do the next one, and then I'm going to stop. So this one, we are looking at a closed interval 0 to 1. Does this one have a maximum or a minimum? What do you want to do? Draw a graph. Okay. So this one, if I start out with 0, can you do 1 divided by 0? No, it's a vertical asymptote there. If I put in a 1, 1 over 1 is 1. I need some more points, don't I? Can I plug in some things between 0 and 1? Like if I put in 1/3. What's 1 divided by 1/3? 3. If I put in a 1/2, we would get out 2. Is this enough for you guys to see what the graph looks like? We said it's like an asymptote here, so it looks like this. 1 if x equals 0. So that's just a closed circle at 0, 1. Does it have an absolute max? No. Does it have an absolute min? Yes. We have 2 of them. F of 0 equals 1 and f of 1 equals 1. Why does this not contradict our theorem? It was a closed interval. It's because of that asymptote. The closed interval method, we had to have a continuous function. Is this function continuous? Can you draw that whole thing without picking up your pencil? No. We had a closed interval, but it wasn't continuous because we had two separate pieces, so that's why it didn't. Okay, tomorrow we will do really just more examples like example 3. Tonight's homework is the book problems, and it's mostly just drawing graphs to meet some requirements, or looking at some graphs and answering questions. So you've got time to work on that now.